What's up, everybody?
Today, we are going to be performing some magic, as well as teaching you the art of becoming an Asian wizard. But without physics, none of the magic would be possible.
Lots of people have tried to play with physics, some with success, and others. Not like that, of course.
So Luce and I both wanted to make a device to break Dr. Bainton's laptop screen, since he has been torturing us for the whole year. And we wanted to do it in the most creative way possible.
Our solution was very simple. We're gonna build a gun.
A gun?
Well, not really a gun, but something close to it. It's called a magnetic linear accelerator, also known as a Gaussian rifle.
Wow, that's really mind-blowing. Get it? Get it?
I don't get it.
This guy.
That is the worst joke ever. Well, to avoid any further bad jokes, we're gonna dive right into how to build the magnetic accelerator right now. So right now, we're going to be performing a demonstration of a magnetic linear accelerator. Let's go! In order to not fail our physicist's ever project,
We decided to use a model of Dr. Bainton's laptop instead of his actual laptop.
wow, that was amazing! Dude, really, that was amazing. I really feel like I'm an Asian wizard right now.
But the simple looking device actually involves quite a lot of physics. With our PhD in physics, we'll be explaining them to you now.
Let's dive right in!
So first, let's explore how the initially non-magnetic ball becomes magnetized and attracted to a magnet.
Oh, is it because of the magical fairies?
Close, but not quite. Initially, the magnetic moments inside the metal ball are disoriented. That is, the electrons of the ball are paired off in opposite pairs, and each electron spin cancels another one's out. This results in no magnetic field being present. However, when the ball approaches the magnet, its magnetic moments begin to align in a direction parallel to the applied field. The permanent magnet causes the metal ball to form an induced magnetic field, making them attracted to each other.
Wait, Dr. Yan. How about let's talk about how energy and momentum are transferred throughout the system?
Of course, Dr. Lin. Go ahead.
When you first look at the magnetic linear accelerator, it seems that it is violating the laws of physics. The law of conservation of energy states that the total energy of an isolated system remains constant. But the metal ball shot out of the end of the accelerator seems like it is gaining its energy out of nowhere.
The truth is that the total energy is indeed conserved. But if the final ball's kinetic energy increased, then what compensates for that increase? Exactly. It's the magnetic potential energy. The trade-off for the increase in the ball's kinetic energy is a decrease in the magnet's field energy. We'll take a closer look at this later.
The Gauss gun also obeys the law of conservation of momentum. When the first ball strikes the first magnet, the forces acting between the two are equal and opposite, as stated by Newton's third law. For every action, there is an equal and opposite reaction. So, F1 equals negative F2. The time that the force acts upon the ball is equal to the time that the force acts upon the magnet, since the force is a result of the interaction between the two. So, if the ball is in contact with the magnet for 0.5 seconds, then the magnet must also be in contact with the ball for 0.5 seconds. So T1 equals T2. The impulse is given by the force multiplied by the change in time. Substituting the values for force and time, you can see that the magnitude of the impulses of the ball and the magnet are equal, only in opposite directions though. By the impulse momentum theorem, the momentum must also be equal. Thus, the law of conservation of momentum holds up.
Now, let's examine the system in more depth. As the trigger ball's distance from the first magnet approaches infinity, the magnetic potential energy on the ball approaches zero. Thus, the closer the ball is to the magnet, the greater the magnetic potential energy.
When the ball is first pushed by hand towards the magnet, it gains kinetic energy. Then, as the ball approaches the magnetic potential energy of the ball increases. This increase in magnetic potential energy is transferred into kinetic energy to allow the ball to speed up, causing the magnetic potential energy to decrease after the ball has gained kinetic energy. This is to make sure energy is conserved. Once the ball collides with the magnet, we can conclude the following. This collision is near elastic since almost no energy has been converted into heat or sound. Therefore, the energy of the first ball is fully transferred to the last ball of the first magnet. This ball is quite far away from the magnet, so it takes little energy to break away from the magnetic attraction. A lot of work is done on the first ball as it rolls towards the magnet, but only a small amount of work is needed for the last ball to break away. This is why the kinetic energy of the final ball ends up becoming much greater than the initial ball's kinetic energy.
Because of this, the greater the amount of magnets, the greater the velocity of the final ball. But of course, only up to a point where the velocity is so great that it breaks the magnet itself. Kind of like when Dr. Bainton grades too many test papers, his head explodes.
And that concludes our little seminar on the magnetic linear accelerator.
We urge you to build your own magnetic linear accelerator at home, as a result is extremely rewarding. That concludes our physics observatory project. Thanks for watching. Stay tuned. have technology!
Wait, SpongeBob! We're not cavemen! We have technology!